Number 2 is a relative motion problem. This is probably the key. Clearly labeled velocity vector diagram. So let's do that first and make sure we get everything correct, and then this problem should work out pretty easily. Alright, so we're given a helicopter can fly 185 kilometers in still air. That's the velocity of the helicopter with respect to the air. The helicopter heads due south. So this is the heading with respect to the air. Okay. After 2 hours of flying, the helicopter is over a point on the ground that is 270 kilometers 40 degrees east of south from where it started. So it's been blown off course. It headed due south and it's ended up 40 degrees east of south. So that's the direction of the velocity of the helicopter with respect to the ground. We don't know its magnitude, but that's the heading of that velocity, and we want to determine the wind velocity. Alright, so let's use this first one. We know both parts about the velocity of the helicopter with respect to the air. So it's going to fly due south. Of course, use north as up. Okay, the other thing to keep in mind is our equation. Velocity of the helicopter with respect to the ground is equal to the velocity of the helicopter with respect to the air plus the velocity of the air with respect to the ground. This is the wind. Alright, so we're saying that if we add this vector, which we just drew right here, I'm going to redraw it, give myself a little more room. So this is the velocity of the helicopter with respect to air, due south and 185 kilometers per hour. Okay, we're told some information about where it ended up. Alright, so I will draw that. It's actually relative to the ground, it's doing something like that. Okay, we also know a time in here, so let's come back to that. Okay, so this is the velocity of the helicopter with respect to the ground. It's given as 40 degrees east or to the right of south. Okay, that's our resultant. This is that one right there. So to get those two, we need to add in our wind vector. We don't know its magnitude, we don't know its angle. So we're going to have theta, velocity of the air with respect to ground. Okay, I drew that theta inside the triangle because I'm going to use this triangle to work through this. We need one more piece of information. Right now we only have one angle in one side of our triangle. Okay, the other piece of information is going to come from this time and this distance. Okay, so I'll switch back to blue. So the velocity of the helicopter with respect to the ground is the distance of the helicopter with respect to ground over the time. And so we know the 270 kilometers. Oops. And we know 2 hours. So it looks like about 135 kilometers per hour. Alright, so now we know two sides of the triangle, 135 kilometers per hour. We need to find both the red magnitude and the angle in here. So I can use, let's see, probably I would use law of cosines to find this red vector first. Alright, so I'll write that out, velocity of air with respect to the ground squared is equal to velocity. Now I'll just write in my numbers. 185 squared plus 135 squared minus 2 times 185 times 135 times the cosine of 40. Okay, so the velocity air with respect to the ground, pull in our calculator. 185 squared. Square root of that. Looks like about 119.1. Pretty strong wind, kilometers per hour. Okay, in my angle, I would probably use law of sines, sine of theta over its opposite side, 135, is equal to sine of 40 over the side I just solved for, 119.1. And that's going to give me a theta of sine 40. Whoa, that didn't work out right. Sine 40 divided by 119.1 times 135 inverse sine. .7 degrees. Okay, so when I write my final answer, here is my velocity, here is my angle. I also need to give a reference for that angle. Alright, so I'm going to write it as 119 kilometers per hour, and I'm going to call it 47 degrees. Okay, that's the theta, this angle right here. So that is east of north. Remember, we always draw our coordinate system here, so north pointing up, so this is east of north.